Okay, so the second talk of this of the second part of the afternoon is Felix Foutel Rodier, who's going to talk about exchangeable coalescent and ultrametric spaces and comps. Felix?
Yeah, thank you, Julien, for the introduction, and many thanks to the organizers for giving me the opportunity to be in front of you now. So what I'm going to talk about is some not so recent work that I did with both of my former PhD advisors, who are Amaury Lambert and Emmanuel, who just talked an hour ago. And it's mainly going to be about those three objects, which, as you will see, are actually three ways of representing a genealogy. Okay, so let me start with the first one. So I'm going to say that a metric space UD is an ultrametric space if it fulfills, the metric D fulfills this reinforced triangular inequality. So this is quite hard to know what's behind that. So actually there is a quite typical way of generating an ultrametric space, which is to start from some rooted real tree. Okay, so space with a tree distance and the distinguished vertex, and to consider the sphere of radius T of that tree. Okay, so you look at the set of points lying at some fixed distance T from the root. Then using the well-known 4-point conditions on DT, you can actually show that this space is an ultrametric space. And I was saying that this construction is typical because actually all ultrametric spaces can be obtained in this way if you allow yourself that the root might be somewhat at infinity. Okay, and so in applications, and especially in population genetics, a rooted real tree is often obtained from a population model where the root corresponds to the ancestor and the tree distance encodes the reproductions in the population. And then distance from the root is often interpreted as time. And this means that an ultrametric space actually corresponds to the genealogy of all individuals living at a fixed time in your model. Okay, and that's why we use them for representing genealogies. So I'm going to be particularly interested into a specific kind of ultrametric spaces, which can be constructed from my second object, which are combs. So what I mean by a comb is a stochastic process, which is CAD-lag, and which is valued into the open subsets of 0, 1. And I'm going to impose that this process is actually non-decreasing for the inclusion. So, okay, so this definition actually generalizes some earlier definition that was given by Amaury and Uribe Bravo in 2017. Okay, so I'm always going to represent combs in this way. Okay, so as a horizontal line which corresponds to the interval 0, 1, and some vertical teeth stemming from this horizontal line. And now if I want to know the open subset at time t, what I do is that I draw a new horizontal line at distance t from the origin. And this line is going to cross some of the teeth of the comb. Okay, and so actually the teeth are going to break the interval 0, 1 into sub-intervals. And I define IT to be the reunion of those sub-intervals. Okay, so you see that I can do that for any time t, and that this property is well fulfilled. Okay, so now how does this picture encode an ultrametric space? But I can now define a distance on 0, 1 by prescribing that the distance between x and y is going to be the first time when x and y lie into the same connected component of IT. And I'm going to call that the comb metric associated to I, sorry. And so there is a more graphical way of understanding this distance, which is that the distance between x and y is nothing but the largest tooth lying between x and y. Okay, so here x and y are at a distance which is given by the height of this tooth. And I was also telling you that there's a connection between trees and ultrametric spaces. And actually, I can draw very easily from this comb representation the tree corresponding to this distance, and it's just given by this tree. Okay, so there's a procedure to do that I'm not going to describe, but it's not very hard. Okay, and so maybe a few examples of concrete examples of combs so that everyone, so that the definition is clear. So let me first describe what we call the Kingman comb. So it's constructed out of an IID sequence of exponential variables. Then you first need to define this TI according to this summation. And so those of you who know Kingman coalescents recognize the waiting times of a Kingman's coalescent. And now what we do is that for each I, I'm going to place a tooth of height Ti located uniformly on 0, 1. Okay, so I place a first tooth of height T2, and this point here is chosen uniformly on 0, 1. Then I do the same for T3, and I can recursively construct then a comb. And the resulting comb is called the Kingman comb, and actually the metric space encoded by this comb corresponds to the completion of a realization of Kingman's coalescent, for those of you who know what it is. Okay, and so now a second very different example, it's what we call the star comb. So now we have an explicit definition, which is that before time 1, the interval partition is just the empty set. Okay, and so this ugly gray rectangle is my representation of the empty set. And now after time 1, the open subset is just the full interval. And it's not very hard to see that the distance associated to this comb is actually the trivial distance where everyone lies at distance 1. And this corresponds to a tree. And this is just the trivial star tree where every branch, you have a single branch that branches into infinitely many new branches at time 1. Okay, so two very different combs that encodes very different ultrametric spaces. So now the question that I want to address now is to know what ultrametric spaces can actually be represented using a comb metric space. So maybe being a bit more precise, what I want to know is that if you give me an ultrametric space, am I able to define a comb and an isometry from the comb metric space to the ultrametric space? And in that case, I'm going to say that I can represent this ultrametric space using a comb. So I have sort of two motivations for doing that. So the first one is that it's quite theoretical, is that the main difference between a plain ultrametric space and the comb metric space is that the latter one actually has an order which it inherits from 0, 1, and that in a sense the tree structure of the space is consistent with that order, in the sense that only adjacent branches can merge. And in the tree literature, finding such an order is actually known as finding a planar embedding of the tree. And so finding a comb representation of an ultrametric space actually amounts to finding a planar embedding of this ultrametric space, which is an interesting question in its own right. But this was actually not our main motivation. Maybe our main motivation was actually that combs really form a very visual framework in which we can study ultrametric spaces. And in particular, if we want to study random ultrametric spaces, the space of combs is just a nice functional space on which we have the square topology and a lot of compactness criterion. Whereas the space of ultrametric spaces is space of metric spaces. Okay, we have some topologies, at least to me, which are a bit more elementary than just the square topology. Okay, so this work was actually kind of a preliminary work before studying more specific models of ultrametric spaces using combs. Okay, and so just to briefly outline the rest of my talk, I'm just going to give the general strategy that we want to apply to put in isometry an ultrametric space and the comb. So the first step is actually that we won't work with the entire ultrametric space, but rather we will consider a sample from the ultrametric space. And we will first show that we can represent this sample in a certain way using a comb. And now all what we need to do is actually to go from the sample to the whole space. And I think that you can believe that in the separable case, this is going to be easy because we can use some kind of density argument. Whereas in the non-separable case, it will require much more work. And for this reason, I will distinguish between the two cases. Okay, so let me start by sampling from a comb. Sorry, sampling from an ultrametric space. So now let me consider some ultrametric space UD. And in addition to that space, I'm going to assume that I have a probability measure that I denote by mu and a sequence xi of IID variables with distribution u. So I'm interested into the metric structure of this sample. Okay, this sample can be seen as a subset of u. So it can be seen as actually a metric space with this distance u. But actually, it's going to be more convenient to encode this metric as a partition valued processes, well, a process valued in the partitions of n, of the integers. And the process is built as follows. So at time t, I'm going to say that I place in the same equivalence class I and j if and only if the distance between xi and xj is lower than t. Okay, the fact that this really defines an equivalence relation is actually a consequence of the ultrametricity of the distance d. So now if I look at the process obtained for all time t, it enjoys two main properties. So the first one is that it's non-decreasing in the sense that if you increase time, then blocks can only merge. And this is a direct consequence of this part of the definition. And the second feature of this process is that its distribution is invariant by the actions of permutations. And we say that it's exchangeable. And from now on, I'm going to call any process that fulfills those two conditions an exchangeable coalescent. So let me just say that here I've introduced these objects as samples from alternative spaces, but they are really interesting objects in their own rights that have received a lot of attention. And for those of you who are familiar with exchangeable coalescents, I just want you to know that I have imposed no Markov property, so that the class of object that I'm looking at is more general than the lambdas or the psi coalescents. Okay, so now let me rephrase this construction, but in the world of comb metric spaces. So now suppose that I have a comb metric space. First of all, this space is naturally endowed with the Lebesgue measure on 0, 1. So it's quite natural to consider that the sampling measures will just be IID uniform random variables on 0, 1. And now if you recall that the distance between 2 points is just the size of the largest tooth between these 2 points, then you can show that this equivalence holds, which is that for 2 points to be at a distance smaller than t, it is sufficient and necessary that they lie in the same interval of the corresponding open subset. And so actually we have a very simple procedure to obtain the coalescent associated to a comb, which I just illustrate in a second, which is that, for example, if you have those sampling variables, you just at time t need to look at what variables fall in the same subinterval of the open subset and place them in the same block. So here they all fall in distinct subintervals, so we have only singletons. But for instance, after this time, U1 and U2 belong to this larger interval, so they are placed into the same block, and you can keep on doing that for all times. So rephrasing what I've just said, actually the partition pi t can be obtained through this relation. So I and j are in the same block, if and only if ui and uj are in the same interval of it. And this definition is actually a well-known construction in the world of exchangeable partitions, which is known as Kingman's pane box construction of an exchangeable partition. And so actually, sampling from a comb can really be seen as a multivariate extension of Kingman's pane box construction that allows to couple this construction for all time t to obtain a coalescent. And so this is a very good news that we are able to link our problem with this construction, because now we can apply Kingman's theorem, which is an important theorem that states that actually all exchangeable partitions can be obtained through this construction. This means that if you give me a partition, I can find you an open subset such that sampling from the open subset leads to the partition. And now it's not that hard to derive our first results, which is the equivalent of Kingman's theorem, but for coalescents. So now if you give me an exchangeable coalescent, I can always find a comb such that sampling from the comb through Kingman's construction leads to the original coalescent. And the proof is not very hard. It's just actually using Kingman's coalescent at some dense subset of 0 infinity, and that gives me a whole set of open intervals. And now I can just use the monotonicity of the coalescent to fill in the gap and just like take limits, right and left limits, to define for all time t the comb. And now it's just technical to check that indeed you recover the original exchangeable coalescent. Okay, so now we know that any exchangeable coalescent can be associated to a comb. And this result directly entails our first representation results for ultrametric spaces, which is that if you give me a separable complete ultrametric space, then I can always find a comb which is isometric to the original space. Okay, and I just need to properly complete this space, and that's not very interesting. So how do we use the previous result to prove this theorem? So first of all, we just need to define a measure on UD, which is such that the measure really charges the whole space, and that we can do it by hand. Now with this measure, we can consider the coalescent associated to this ultrametric space. We can use now our version of Kingman's theorem to find a comb representing this coalescent. And now, all what we need to do is to use some kind of density argument to show that there is enough information in this coalescent to recover the whole structure of the ultrametric space UD. And in our setting, we can use a result due to Gromov, which is often referred to as Gromov reconstruction theorem, and which directly gives us the isometry between the comb metric space and UD. Okay, so now I could have stopped there and said that we are able to represent all coalescents and all separable ultrametric spaces, and that those are actually the only interesting spaces. And this would have been fair because in most of the studies on random metric spaces, you need to assume those two assumptions. Okay, but actually, if you look at what are the combs which are separables, you can, okay, sorry. So now I'm taking a comb, the corresponding metric and the corresponding coalescent. And there's actually an equivalence between this comb being separable and the interval IT having full Lebesgue measure for all time t. And in terms of the coalescent, this translates into this condition, which is that pi t never has singletons. And this latter condition is actually quite well known in the world of exchangeable partitions, and it's called absence of dust. So you see that if we restrict our attention to combs that are separable, we actually completely miss a whole class of coalescents, which are those coalescents that have dust. And so starting from this observation, which is not due to us, we were wondering with Amaury and Emmanuel if we could actually try to consider to work without separability and to be able to show that all coalescents can be obtained by sampling from ultrametric spaces, and to state maybe a weaker representation results for the combs representation of ultrametric spaces. Okay, so separability is very natural for metric spaces. It's not natural for coalescents because dust is something that we know how to handle. And so in the remaining time, I won't have time to state our result that we obtain for non-separable spaces because it's slightly technical, but I just want to maybe to show you the difficulty that arises when you want to consider a non-separable metric space. So the main issue that we encountered can be summarized into the following fact, which is if you consider the Borel sigma field of a non-separable metric space, then it's extremely large, and this means that you can define fewer measures on it. Okay? And so, in particular, the question of knowing if you can represent a coalescent with dust requires to find some measure defined on a non-separable ultrametric space, and we know that it's difficult to define measures on non-separable metric spaces. Okay, so being a bit more precise, I'm going to come back to the example of the star comb. Okay, so this was the comb associated to the star tree. And so first of all, it's not hard to see that the associated coalescent is quite trivial. Before time 1, every integer is in a singleton block. And after time 1, everyone merges into a single block containing all the integers. And on the other end, we know that the comb metric is this trivial distance, and that this generates the discrete topology. And so in particular, the Borel sigma field associated to this distance is just all subsets of 0, 1. So now if we try to guess how should be a measure defined on 0, 1, a measure that would lead to this coalescent, then you see that every time you sample a new point, you should end up in a different leaf of the tree so that all integers are in singletons. And actually, this shows that the measure mu should be diffuse, because if you have an atom, then you will sample many times in that atom and you will see a macroscopic block at that time. And so now the question of knowing if we can find a measure that represents this coalescent actually amounts to knowing if we can define a diffuse measure, but which is defined on all subsets of 0, 1. And actually, this question is quite well studied, and it is called the Banach-Ulam problem in measure theory, the problem of finding measures that are diffuse and defined on all subsets of some given set. And so quite surprisingly, we're able to show the following results. So this result states that if you can find one ultrametric space with a measure such that the corresponding coalescent has dust, then you can always represent a coalescence with dust as samples from ultrametric spaces, and then you can find an extension of the Lebesgue measure to all subsets of R. Okay. And so most of you might know that there is no answer to this third point, and that actually really depends on the axioms that you choose. And I don't want to go into too many details, but we can actually link the existence of such an extension to the existence of some large cardinal, which is inaccessible and which is called a measurable cardinal. And we know that assuming that such a large cardinal exists, it actually has a greater consistency strength than the usual ZFC axioms of set theory. So this means that if we want to be able to answer our very simple questions on coalescence, then we need to assume something that we really don't want to assume actually, which is the existence of some very large and very weird cardinal. And so the way out of that, because obviously we do not want to go into that direction, is that actually we want to allow the sampling measure to be defined on some smaller sigma field, which will be intermediate between the very large Borel sigma field on which we have few measures and the very little sigma field generated by the balls on which we have few measurable functions. And so we want this sigma field to be intermediate between these two. And I won't state any rigorous results, but if we do so, then we remove the previous problem and we are actually able to always find, regardless of the axioms that we choose, enough measures to first be able to represent any coalescent as a sample from an ultrametric space, and second, to represent any ultrametric measure space according to a comb. But then we have to give a weaker definition of the isometry because we cannot put in isometry the two spaces. Okay, so wrapping up. So I've introduced a new object, which are those combs, and that appear both naturally as planar representation of ultrametric spaces, and also they appear in exchangeability theory as an extension of Kingman-Spain box construction for exchangeable coalescents. So now those combs seem to be quite natural because any coalescent can be represented using a comb, and also any separable ultrametric space is isometric to some comb metric space. And as I was telling you, we try to do some things in the non-separable case, but this, if you do that, you actually face some very deep issues from measure theory. And we proposed a way out of that. And in that case, we're able to provide a representation of non-separable ultrametric spaces as combs. And I just end up with a few remarks that I didn't have time to mention. So the first one is that all of this work is about ordering things. And we've made an extensive use of the notion of composition, which is the ordered version of a partition. And there are some works that are done on exchangeable partitions due to Gnadin. So the second remark I want to do is that we've studied like coalescence in general, but of course, most people are interested into lambda coalescence. And in that case, the comb associated to a lambda coalescent is actually a Markov process, and it enjoys a lot of nice properties, and we can compute its transition in terms of the measure lambda. And there's actually a very direct construction from the flow of bridges of Bertrand and Le Gall. And so finally, our original motivation was actually to study comb-valued processes, genealogy values processes, that is, genealogies that evolve with time. And actually, those can be represented now as comb-valued processes. And we were, again, quite successful in showing that the semigroup of a comb-valued process, for instance, that associated to Kingman's coalescent, can actually be described quite explicitly using a cutting and pasting procedure. Okay, so I hope I'm not too much over time, and thank you for your attention.
Okay, thanks a lot, Felix. Questions? Okay, so we have two at the same time. So let's start with Stefan, maybe. Stephen, are you able to unmute yourself and ask your question, or do you want to ask it in the chat, or was it
I think maybe he was clapping.
Okay, so Pascal then.
Yes, thanks, Felix. I learned many things, and I learned in particular that it's interesting to study exchangeable coalescents, which are not Markov processes. So are there some examples of forward models that have these as genealogies?
Yeah, we've not thought about it too much, but maybe a bad example is the coalescent associated to branching processes, which is not Markovian. But somewhat, if you give yourself the size of the population, then it becomes Markovian. So it's maybe a bad example. No, I must say that no, we do not have a canonical example of any Markovian interesting exchangeable coalescence, except maybe the star tree, which is quite neutral in a sense.
I couldn't hear you very well. I'm sorry.
Sorry. I was saying that we do not have a canonical example of a non-Markovian coalescent, except maybe those associated with branching processes. So you condition a branching process on having, for instance, more than n individuals, and you sample n of them. Backward in time, you have something which is not Markovian, but which remains exchangeable. But we know that we have other ways of representing these objects. The coalescent framework is not the most natural one.
Okay. So can I ask just one quick thing, but just as an example to try to understand. So what would the comb process be for the evolving genealogies in the Kingman case?
Yeah, okay, it's a very good question. So of course, at one time you have a Kingman coalescent, and so now if you move time on, it's as if the teeth are growing at constant speed, and that's just aging of the process.
Yeah.
Now any family is gonna the size of any family is going to follow a small Wright-Fisher diffusion.
Yeah.
As the comb of your teeth, we're following a multi-dimensional version of the Wright-Fisher diffusion.
Sure.
Now, upon collision, this means that you have a family that dies out. So upon collision, you only retain the largest tooth.
They coalesce, okay.
Yeah, they coalesce and you retain the largest one. And you have some sort of appearance of infinitesimal teeth at the origin at a constant rate, which corresponds to birth of new small families.
Okay, but do you have okay. So there is no measure because they are born with zero lengths, right?
Yeah, they are born with zero lengths. But if now, so this was kind of the generator of the process, but now if you want to know the semigroups, if you look at time t and you want to know time t process, then it's quite easy. You just have to sample an independent Kingman comb between time t and t possess.
Yeah.
And now you just cut all teeth that lie before time t, okay? And you resample them into your comb at time in the past. Yeah, this would be easier to explain with a picture, but there is like a very simple procedure to generate the semigroup.
Yeah, that's very nice.
Hi, Felix. I want to ask a question, a quick one.
Yeah.
Sorry if I got confused, but I was wondering, in your representation using quants for the this ultrametric space, are the quants deterministic, or you're actually working with random quants? I'm sorry, I think I got confused in the middle, but I just want to understand the main result.
Sorry, is your question? Sorry, I don't think.
Combs, is your combs IT is a random object?
Yeah, yeah.
Or
but it's both. I mean, it's if you look at a fixed realization, then it's not random and it corresponds to a deterministic ultrametric space. But of course, you can define a random comb, and that's what we are interested in. And in that case, you have exactly, you have like a framework to deal with like random ultrametric spaces, but which only involves some squirrel code topology and not the Gromov type topologies of metric spaces.
Okay. Okay.
Okay, so I propose that we unmute yourself to thank again Felix. And if I'm not mistaken, we have a short break now.
Right.
Yeah.
Yep.
So we can all meet in the other town and come back in 15 minutes.